So, you've heard the noise, you've seen the headlines. Generative AI is not just another tech trend, it's a full-blown revolution. Right now, we are in the middle of a digital gold rush. This isn't about hype or buzzwords anymore. This is about building real-world applications that are changing how we work. This is about building real-world applications that are changing how we create. This is about building real-world applications that are changing how we even think. Large language models, or LLMs, are the powerful engines driving this entire movement. They are the new bedrock of software development. Engineers who know how to wield them are becoming the most sought-after professionals in tech. If you've been wondering if it's too late to jump in, you are right on time. The demand for AI engineers, especially those skilled in LLMs, has absolutely skyrocketed. Companies, tiny startups, companies, massive tech giants, all are scrambling to integrate this technology into their products. They're building smarter chatbots. They're building more intuitive coding assistants. They're building hyper-personalized content generators. This isn't just about adding a cool feature. It's a fundamental shift in user experience and capability. Understanding how to build with these models is no longer a niche skill. It's quickly becoming a core competency for any serious software engineer. The opportunities are massive. The barrier to entry is lower than you think. You don't need a PhD in machine learning to get started. You just need the right map. Think about the apps you use every day. Soon, almost all of them will have a layer of intelligence powered by LLMs. That search bar that understands exactly what you mean, not just what you type. That's LLMs. That customer support chat that solves your problem instantly without making you wait. That's LLMs. That tool that helps you write better code, faster than ever before? You guessed it, LLMs. This technology is becoming the new electrical grid for the internet. Learning how to plug into it is the single most valuable investment you can make in your career today. 2024, 0524. We're talking about a paradigm shift. You have a front row seat. In this video, I'm going to give you that map. We're going to cut through all the noise and get straight to the practical skills you need. This isn't a high-level university lecture. This is a hands-on, engineer-to-engineer guide. From understanding the core concepts to building your own powerful AI applications, we'll cover everything you need to know from the ground up. We're going to move fast. We're going to get technical. And by the end of this, you'll have a clear, actionable plan to start building with the most exciting technology of our generation. So buckle up, because your journey into the world of applied AI starts right now. So what exactly are we going to cover? I've designed a rapid-fire journey to get you up to speed in record time. Here's the roadmap. We'll start at the very beginning, the transformer. We'll break down how it works and why it was such a game changer, leading to powerful models like the GPT family. We're going to demystify these core concepts so you understand not just the what, but the why. This foundational knowledge is crucial. It's the bedrock everything is built on. You'll see how these models learn to understand and generate human-like text. From there, we'll dive into the practical side. This is where the magic really happens. We'll explore the art and science of prompt engineering. Then we'll get into embeddings, and vector databases, VectorDB. This is the secret sauce for giving LLMs long-term memory and the ability to work with your own custom data. We'll look at key players like Pinecone, ChromaDB, and FAISS. I'll show you how they create a searchable brain for your AI applications. Next, we'll assemble these pieces into Retrieval Augmented Generation, RAG. It's one of the most important patterns right now, allowing you to build hyper-intelligent support chatbots and research assistants that answer questions from documents. We'll then look at essential tools and frameworks like LangChain, LlamaIndex. We'll also cover how to use major APIs from OpenAI, Anthropic, and Google's Gemini. Finally, we'll look at the future, AI agents. Agents that can use tools, agents that reason, and agents that take actions to accomplish complex goals. We'll walk through architectures for real projects, an AI coding assistant, a YouTube content generator, an AI financial advisor, and more. By the end of our 18 minutes, you won't just be an informed spectator, you'll be an equipped builder ready to stake your claim in the AI revolution. Let's get started. Alright, let's get right into the nuts and bolts. To understand how we got to models like GPT-4, start with the paper that changed everything. Attention is all you need. In 2017, researchers at Google introduced the transformer. Before that, go-to sequence models were RNNs and LSTMs. RNNs, LSTMs. Those models processed words one by one, left to right. That sequential nature was both strength and weakness. It made training slow and hurt long-range memory. The transformer flipped this on its head. It was designed for parallelization. Instead of sequential processing, it looks at all words at once. Massive breakthrough. Imagine reading a whole page at once instead of one word at a time. That leap let us train much larger models on far bigger datasets, faster. It unlocked the scale of today's LLMs. Key components: encoder and decoder. Encoder. Think of the encoder as reading and understanding the input, creating rich numerical representations. Decoder. The decoder takes that representation and generates the output, word by word. For example, in translation, the encoder reads English, and the decoder writes the sentence in French. This encoder-decoder structure became the blueprint for a new generation of AI. The new architecture also made models smarter. Simultaneous processing builds stronger relationships across words. It solved long-range dependency problems. It enabled tasks like translate languages, write coherent essays, generate creative code, hold nuanced conversations. Every major LLM you hear about today, GPT, Gemini, Llama, Claude, is built on the foundation of the transformer architecture. Understanding it is the first step to mastering modern AI. So if the transformer can look at all the words in a sentence at once, how does it know which words are important? How does it figure out the relationships between them? The answer lies in the title of that famous paper, Attention is All You Need. The self-attention mechanism is the secret sauce, the absolute heart of the transformer. It's a brilliant mechanism that allows the model to weigh the importance of different words in the input text when it's processing a specific word. It helps the model understand context by figuring out which other words are most relevant to the current word it's looking at. This is how it learns grammar. This is how it learns syntax. This is how it learns a whole lot of nuance. Let's break that down with a simple example. Take the sentence. The robot picked up the heavy metal ball because it was too strong. What does it refer to? The robot or the ball? For a human, the answer is obvious. It's the robot. But for a machine, this is a classic ambiguity problem. An attention mechanism solves this by creating a query for the word it, and then scoring its relationship against every other word in the sentence. It will learn to assign a very high attention score between it and robot, effectively linking them together. It understands that strong is associated with robot, not the ball, and therefore it must be the robot. This process happens for every single word in the sentence. For each word, the model calculates how much attention it should pay to all the other words, including itself. This creates a rich, dynamic map of contextual relationships within the text. It's not just about one word, it's about how every word relates to every other word. This happens in multiple layers, and with multiple attention heads. Each head looks for different kinds of relationships. Together, they create an incredibly deep and nuanced understanding of the text. This is fundamentally different and more powerful than the context mechanisms of older models. RNNs tried to pass context along in a hidden state, which would get diluted over long sequences. Attention, on the other hand, provides direct, dynamic connections between any two words in the sequence, regardless of their distance. This ability to directly model relationships between all words is what allows transformers to handle long, complex sentences and documents without losing the plot. It's the core computational step that gives LLMs their remarkable ability to understand and generate text that feels so uncannily human. It really is the magic ingredient. Once the transformer architecture was unleashed, it was only a matter of time before someone scaled it up. That's where OpenAI and the GPT family come in. GPT stands for Generative Pre-trained Transformer. Generative means its primary purpose is to generate new text. Pre-trained means it's been trained on a massive corpus of text. Transformer, of course, refers to the architecture we just discussed, specifically using the decoder part of it. Trained on the internet, books, and other sources. From that training, it learned grammar, facts, reasoning abilities, and different styles of writing. The GPT series started with GPT-1 in 2018, which was impressive, but flew relatively under the radar. Then came GPT-2 in 2019, and things got serious. GPT-2 was so good at generating coherent text that OpenAI initially withheld the full model, citing concerns about potential misuse for generating fake news. This was a wake-up call for the world. The real game-changer, however, was GPT-3 in 2020. With 175 billion parameters, it was an order of magnitude larger than anything that came before it. It could write code, answer questions, translate languages, and more, all with minimal instruction. The innovation of GPT-3 wasn't just its size, it was the discovery of in-context learning. Researchers found you didn't need to fine-tune the model for every new task. Instead, you could just describe the task in the prompt itself and provide a few examples. A technique called few-shot prompting. For instance, you could show it a few English to French translations, and it would understand that you now wanted it to be a translator. This made the model incredibly versatile. The latest in the public line, GPT-4, is even more capable, with improved reasoning, creativity, and the ability to understand images as well as text. This dynasty of models demonstrates a clear trend. As you scale up model size and training data, new emergent abilities appear. The GPT models are a clear demonstration of the power of scale applied to the transformer architecture. They've evolved from interesting text generators into powerful general-purpose reasoning engines that form the backbone of countless applications, from ChatGPT itself to AI-powered features in products you use every day. They represent a specific and highly successful implementation of the transformer idea, focusing on the decoder half to become masters of text generation. Understanding this history is key to appreciating how we arrived at the current moment and where the technology is likely to head next, towards even larger, more capable, and more integrated models. So you have access to these incredibly powerful GPT models. Now what? You can't just expect them to read your mind. You need to tell them what you want, and how you tell them matters a lot. This is where prompt engineering comes in. It's the art and science of crafting the perfect input, the prompt, to guide an LLM to produce the exact output you're looking for. Think of it as being a skilled manager or a director. You're not doing the work yourself, but you are giving precise, clear, and effective instructions to an extremely capable but very literal-minded assistant. The quality of your output is directly proportional to the quality of your prompt. In the early days of GPT-3, prompts were often simple questions or commands. But prompting has become much more sophisticated. A good prompt often includes several key components. First, a role. You are an expert Python programmer. Second, the task. Write a function that takes a list of strings and returns the list sorted by length. Third, context. Provide any necessary background information, data, or constraints. Let's look at a concrete example. Split screen. Left vague prompt versus right detailed prompt. Instead of explain the transformer, a much better prompt would be, you are a senior AI engineer creating a presentation for new software developers. Explain the transformer architecture in 3 short paragraphs. Start by contrasting it with RNNs. Use the analogy of reading a whole page versus 1 word at a time. Keep the tone educational but accessible. See the difference? We've given it a role, clear task, and specific constraints on format, content, and tone. This level of detail dramatically reduces ambiguity and guides the model toward the desired result. Here's a quick coding tip that illustrates this perfectly. When asking an LLM to generate code, always frame your request within code comments. For example, instead of write a Python function to calculate factorial, write it out like this: def factorial n. Implement a recursive function to calculate the factorial of n. Handle the base case where n is 0. This technique, called code style prompting, signals to the model that you expect a code block as output and helps it fill in the blanks correctly. It's a small change that makes a huge difference. Mastering prompt engineering is a critical skill for any developer working with LLMs. It's the new command line for the age of AI. We've seen how powerful pre-trained transformers like GPT-4 are. They have a vast, generalized knowledge of the world, learned from their massive training data. But they have two major limitations you'll hit almost immediately when building a real-world app. The first is the knowledge cutoff. A model like GPT-4 was trained on data up to a certain date. It knows nothing about events. It knows nothing about products. It knows nothing about information that appeared after that date. As of today, May 24th, 2024, it wouldn't know the winner of a sports championship that happened yesterday. It's like a brilliant historian locked in a library that hasn't received new books in over a year. The second, and perhaps bigger problem, is the lack of specific context. These models have no knowledge of your private, proprietary data, your company's internal wiki, the specifics of your product documentation, the history of your customer support tickets. You can't ask it, what was the resolution for customer ticket number 7839? Because it has never seen that ticket. It has no access to your internal world. This is a huge barrier. To build truly useful applications, a customer support bot, an internal research assistant, the LLM needs to be able to access and reason about your specific, up-to-date information. It needs a memory that extends beyond its initial training. One common but flawed approach is trying to stuff all the relevant information into the prompt. This is called in-context learning. It works for small amounts of data, but it quickly falls apart at scale. LLMs have a limited context window, a maximum amount of text they can consider at one time. Older models, a few thousand words. Newer models from Anthropic and Google, up to 1 million tokens. Even so, it's still not a scalable solution. You can't fit your entire company's documentation or a whole book into the prompt every single time you ask a question. It's inefficient, it's expensive, and often impossible. This is the core challenge that leads us to the next layer of the AI stack. We need a way to give the LLM access to a vast external knowledge base on demand. We need a mechanism to find the exact, relevant pieces of information from our private data and then provide only those pieces to the LLM as context. This process, retrieving relevant information and augmenting the LLM's prompt with it, is the key to building knowledgeable, trustworthy, domain-specific AI. It's how we give the LLM an open book exam, where the book contains all of our custom data. Section 2. Embeddings. Translating meaning into math. So, how do we search through millions of documents to find the right piece of information for the LLM? A simple keyword search won't cut it. Keyword searches are brittle. They only find exact words. If a user asks, "How much does it cost to ship to Lagos?" but your documentation says, "Our delivery fees for Nigeria are listed here," a keyword search for cost or ship would likely fail. We need semantic search, not keyword search. This is where embeddings come in. They are the cornerstone of modern search, and the first step in giving our AI a better memory. An embedding is a numerical representation of data, like text. It's a list of numbers, a vector. It captures the semantic essence of that data. You can create an embedding for a single word. You can create an embedding for a sentence. You can create an embedding for a paragraph. You can create an embedding for a whole document. These vectors are generated by deep learning models, often a specialized part of a transformer. In this way, pieces of text with similar meanings get mathematically similar vectors. Think of it like a sophisticated coordinate system for meaning. In this system, king and queen would be close together. Now imagine, king minus man plus woman results in a vector very close to queen. This famous example shows how vectors capture complex relationships. It's not just synonyms, it's about context and relationships. The word bank has different vectors in riverbank and investment bank. The embedding model uses surrounding words to build a context-aware representation. To prepare custom data, first chop it into manageable chunks, maybe paragraphs or sections. Then use an embedding model via APIs like Text Embedding 3 Small or via open-source libraries. Convert each chunk into a vector embedding. Store these vectors, creating a library of meaning. Now, instead of raw text documents, we have numerical vectors. Each vector is a compressed mathematical representation of meaning. This process is the critical first step in building a searchable knowledge base for our LLM. Section 3. Vector databases. The AI's long-term memory. Okay, so we've turned our documents into a massive collection of numerical vectors, embeddings. Now what? Where do we store them? You can't just put millions of high-dimensional vectors into a traditional SQL database. A traditional database is built for exact matches on structured data, like a user ID. It isn't made to find similar vectors in a 1036-dimensional space. Doing that would mean comparing a query to every other vector, which becomes impossibly slow as your data grows. We need a new kind of database, purpose-built for this task. This is where vector databases come in. Diagram text chunks, vectors, stored in a vector database. A vector database stores and manages embeddings, and most importantly, efficiently searches huge quantities of high-dimensional vectors. Think of it as a highly optimized library for embeddings. When you store a vector, you're not just saving numbers. The database builds an index organizing vectors by proximity. That index lets it do incredibly fast similarity searches without comparing your query to every single item. It's the infrastructure that makes semantic search possible at scale. They use techniques like hierarchical navigable small worlds, HNSW, inverted file indexes, IVF. You don't need to master the algorithms. They use clever shortcuts to quickly narrow the search space. It's like a super efficient GPS for meaning. It finds the right neighborhood, then the right street, speeding up nearest neighbor search. That's how they return results from billions of items in milliseconds. Several key players have emerged. Pinecone, a fully managed cloud solution, high performance, easy to use. ChromaDB, open source, easy to start, runnable locally or in the cloud. FAISS, an open source library from Meta that provides core similarity algorithms. Many other databases, including PostgreSQL with the PG vector extension, now have vector search. Choose based on scale, budget, and infrastructure. But they all serve the same purpose: the long-term searchable memory for your AI. Section 4. Finding meaning with similarity. Now we have all the pieces in place. We have our knowledge base, the company's internal documentation, chopped into chunks. We've used an embedding model to convert each chunk into a vector. We've stored those vectors in a vector database like Pinecone or ChromaDB. A user comes to our support chatbot. How do I reset my two-factor authentication? How do we use our system to find the answer? Retrieval augmented generation shines here. It all starts with a similarity search. Step 1. Convert the user's query into a vector embedding. Use the exact same embedding model we used for documents. You must use the same model. Crucial to keep vectors in the same meaning space. The query vector is a numerical representation of the user's question. It's our search probe, a guide through the documentation library. It captures semantic meaning, not just specific words. Send this query vector to the vector database. Ask the database. Find the top k vectors most similar to this query. K is a number we choose, 3, 5, 10. The DB uses indexing algorithms like HNSW to search very quickly. It computes distance or similarity between the query and indexed vectors. The common metric is cosine similarity, measuring the angle between vectors. Vectors pointing the same direction are semantically similar. The DB returns closest matching vectors plus original content and a similarity score. Example, top 3 chunks returned. Resetting your two-factor authentication device. Paragraph. FAQ. Lost phone and account access. Section. Step-by-step guide. Updating your security settings. They might not contain the exact phrase, "How do I reset?" but they're semantically relevant. We've retrieved the most relevant context from our entire knowledge base in milliseconds. Section 5. RAG. The ultimate open book exam. We've successfully retrieved the most relevant chunks of text from our knowledge base. We have the user's original question, and we have a handful of highly relevant context snippets. What do we do now? We can't just dump this text back to the user. That would be a clunky search engine, not an intelligent chatbot. This is the final and most crucial step, where we bring the large language model back into the picture. We are now ready to perform Retrieval Augmented Generation, or RAG, user query, embed, vector DB search, retrieve top K chunks, prompt template, LLM, final answer. This is the architectural pattern that combines the power of retrieval with the generative power of an LLM. The core idea of RAG is to construct a new, very detailed prompt for the LLM. This prompt is carefully assembled from the pieces we've gathered. First, we provide some instructions to the LLM, setting the context. You are a helpful support assistant. Answer the user's question based only on the provided context. If the context doesn't contain the answer, say you don't know. This instruction is critical for preventing the model from hallucinating or making up answers based on its general knowledge. We are forcing it to act like a student in an open book exam, using only the materials we've given it. Next, in that same prompt, we insert the context we retrieved from our vector database. Context. We paste in the 3 to 5 paragraphs our similarity search identified as most relevant. Finally, we append the user's original question, perhaps under question, persona it should adopt, the source material it must use, and the specific question it needs to answer. We've effectively given the LLM a hyper-relevant, bite-sized portion of our knowledge base to work with. The LLM then reads this entire prompt and does what it does best. It synthesizes the information and generates a natural, human-like response. It will read the question and the provided context and formulate a direct answer. For our user who asked about resetting their two-factor authentication, the LLM might generate a response like, "To reset your two-factor authentication, you can follow the steps in our guide for updating your security settings." I found a section that says, "This RAG pattern is incredibly powerful. It allows us to build applications that are accurate, up-to-date, and grounded in a specific body of knowledge, effectively overcoming the memory and knowledge cutoff problems of standalone LLMs." Section 1. The AI Developers Toolkit, LangChain and LlamaIndex. Alright, so we've covered the core concepts, transformers, embeddings, vector databases, the powerful RAG architecture. Now, how do we actually build all of this without writing thousands of lines of boilerplate code from scratch? This is where orchestration frameworks come into play. And the two biggest names you need to know are LangChain and LlamaIndex. LangChain and LlamaIndex. Chains, prompts, models. These are not competing tools. They are powerful libraries that provide the essential building blocks, the plumbing, for creating sophisticated LLM applications. They abstract away the complexity of chaining together different components like models, prompts, data sources, letting you focus on the logic of your application. LangChain is like a Swiss Army knife for LLM development. It's an incredibly comprehensive open-source framework that provides modular components for virtually every step we've discussed. It has integrations for hundreds of LLM APIs, dozens of vector databases, and all sorts of data loaders for ingesting different file types. LangChain introduces the concept of chains, which are sequences of operations. For example, you can create a RAG chain that automatically takes a user query, retrieves relevant documents from a vector store, formats a prompt with that context, and then calls an LLM to get the final answer. It provides a high-level, declarative way to build complex logic. LlamaIndex, on the other hand, started with a more focused mission, although it has since expanded. Its primary focus is on the data part of the equation, specifically on making your private data easily accessible to LLMs. While LangChain is a general-purpose tool for building with LLMs, LlamaIndex excels at the data ingestion and retrieval steps of the RAG pipeline. It offers highly optimized data connectors for pulling in information from sources like PDFs, Notion, Slack, databases, and it provides sophisticated indexing and query engine capabilities. You can think of LlamaIndex as a specialist in building the best possible retrieval system, while LangChain is the generalist for orchestrating the entire application around it. The great news is that these tools work wonderfully together. It's very common to see developers using LlamaIndex to build a powerful, optimized query engine for their data, and then plugging that engine into a larger, more complex application, orchestrated by LangChain. These frameworks are not magic. They are toolkits that save you an immense amount of time and effort. They provide standardized interfaces and pre-built components that let you experiment and iterate on your ideas much faster. Learning to use them effectively is a crucial step in moving from understanding the theory of LLMs to becoming a productive, real-world AI application developer. Section 2. The API Buffet, OpenAI, Anthropic, and Gemini. Now that you have your orchestration framework, you need an engine. You need the actual large language model. Unless you have millions of dollars and a team of researchers to train your own model from scratch, you'll be using a model provided by one of the major AI labs via an API. This is fantastic news. State-of-the-art AI is available to any developer with an internet connection and an API key. The three dominant players right now are OpenAI, Anthropic, Google. Each offers a suite of models with different strengths, capabilities, and pricing, creating a competitive market that benefits developers. OpenAI kicked off the revolution with GPT. Their APIs include GPT 3.5 Turbo, GPT-4, and are popular, well-documented, supported by tools like LangChain. OpenAI's models are excellent all-rounders, strong at reasoning and following instructions. Anthropic was founded by former OpenAI researchers. Their model family is called Claude. Anthropic emphasizes AI safety and builds models that are more helpful, harmless, honest. Claude 3 comes in Haiku, Sonnet, Opus, offering trade-offs in speed, cost, intelligence. Claude's massive context window reached 200,000 tokens, great for summarizing and reasoning over very large documents. Developers use Claude for creative writing and nuanced conversation. Google brings the Gemini family. Google is a pioneer of transformers and a research heavyweight. Gemini 1.5 Pro is an example. A powerful multimodal model understands text, images, audio, video in one prompt. Gemini 1.5 Pro also introduced a 1 million token context window, a new industry standard. Competition between OpenAI, Anthropic, Google is fierce and great for developers. Models are getting better, cheaper, more accessible, giving you a buffet of AI engines to choose from. We've talked about RAG, which is a powerful pattern for answering questions based on knowledge. But what if you want your AI to do more than just talk? What if you want it to take actions? What if you want it to browse the web? What if you want it to run code? What if you want it to use other software tools? This is the next frontier in applied AI. AI agents. An AI agent uses an LLM as its reasoning engine. It uses a set of tools to execute decisions in a loop. It's the difference between an AI that can tell you how to book a flight and an AI that can actually book the flight for you. The core loop is described by the REACT framework: reason and act. Show. Goal. Thought. LLM reasons. Action. LLM chooses a tool. Observation. Tool's output. Thought example. Goal. Find the current price of Apple stock and tell me if it's higher or lower than it was 30 days ago. LLM thought, I need the current stock price. LLM thought, I need the price from 30 days ago. LLM thought, I need to compare them. Based on this, the agent decides to take an action. It chooses a tool, e.g., Stock Price Checker. It executes Stock Price Checker, tickers, AAPL, dates today. The tool runs and returns an observation, the current stock price. That observation is fed back into the agent's prompt. The LLM sees the original goal. The LLM sees its previous thoughts. The LLM sees the new information. It reasons again, I have the current price. Then, I need the price from 30 days ago. It calls Stock Price Checker, ticker, AAPL, date, 30 days ago. Thought, action, observation. The loop continues until it has enough data. Then the agent stops using tools and generates the final answer for the user. Frameworks like LangChain provide support to build and manage these loops. This is a massive leap beyond simple chatbots. Agents can interact with the digital world to complete complex, multi-step tasks. A shift from AI as a knowledge repository to AI as an active participant and software automation. Section 4. Project Blueprints. Building your first AI assistant. Let's make this concrete by sketching out the architecture for a few powerful AI agent projects you can build today. First, an AI coding assistant. The goal is to create an assistant that can not only write code, read your existing files, understand the project structure, and run tests. The core would be an LLM agent. Its tools would include a file reader tool to read the contents of specific files, a file writer tool to create or modify code, and a terminal tool to execute shell commands like running a linter or a test suite. A user could then request, refactor the user service.py file to use async functions, and then run the tests to make sure nothing broke. The agent would then reason, read the file, write the changes, and execute the tests. A quick coding tip: always wrap your terminal tool in a sandboxed environment like a Docker container to prevent the LLM from executing malicious commands on your host machine. Next, let's consider an AI YouTube content generator. The goal here is to automate the research and scripting process for creating a video. The agent's mission might be: create a script for a 5-minute video about the benefits of intermittent fasting. The agent would have a set of tools designed for content creation: web search tool, YouTube search tool, and perhaps a text chunk summarizer tool. The agent would first search the web and YouTube, then use the summarizer to distill the key points, and finally synthesize all that information into a coherent video script. How about an AI financial advisor? This is a more sensitive application, so it requires more care. The goal is to create a RAG-based agent that can answer questions about market trends and analyze a user's portfolio. First, you'd use a RAG system to ground the model in up-to-date, reliable financial data. Portfolio Analyzer, Market News Retriever. The key here is that the agent primarily uses retrieval to provide information. A crucial safety tip: always include prominent disclaimers. Finally, an AI research assistant. This is a classic agent application. Imagine you're a student or a professional who needs to write a paper. The goal: gather 5 peer-reviewed papers. The agent's tools would be indispensable: a scholar search tool, a PDF reader tool, and a summarizer tool. The agent would search for the papers, download and read them, and then generate the required summaries. The coding tip here is to implement robust error handling, as external APIs and file downloads can often fail, and the agent needs to be able to retry or report the failure gracefully. Section 5. The Grand Vision: Autonomous Systems in the Real World. These project blueprints, the coding assistant, the content creator, the financial analyst, the research assistant, are not just theoretical exercises. They are the building blocks of a much larger vision: the creation of autonomous systems that can handle complex, long-running tasks with minimal human intervention. We are moving from simple, single-shot commands to a world where we can delegate entire workflows to AI agents. The current generation of agents, built with frameworks like LangChain, are the early pioneers in this space. They still require careful setup, well-defined tools, a good amount of human oversight to work effectively and safely. The next evolution of this technology, which is already being heavily researched, involves agents that can learn and adapt. Imagine an AI coding assistant that, after you correct its code a few times, learns your preferred coding style and automatically adopts it in the future. Or a research assistant that learns which academic sources you trust most and prioritizes them in its searches. This involves incorporating memory and feedback loops not just within a single session, but across multiple interactions over time. These future agents won't just use tools, they will learn how to use them better and may even be able to create new tools for themselves by writing their own code. This leads to the concept of multi-agent systems, where different specialized agents collaborate to solve a problem that is too complex for any single agent to handle on its own. Imagine a CEO agent that receives a high-level business goal, like increase user engagement by 10% this quarter. This agent might then delegate tasks to a data analyst agent to find areas of low engagement, a content strategist agent to brainstorm campaign ideas, and a software engineer agent to implement the necessary product changes. Each agent would work on its subtask, reporting its progress back to the orchestrating agent, creating a kind of autonomous digital company. Of course, this grand vision comes with enormous technical and ethical challenges that we are only just beginning to grapple with. How do we ensure these systems are aligned with human values? How do we prevent them from causing unintended harm? How do we build robust containment and oversight mechanisms? As engineers building these foundational systems, it is our responsibility to think about these questions from day one. The journey from simple RAG systems to fully autonomous agents is one of the most exciting and consequential frontiers in technology. By understanding the tools, APIs, and agentic patterns of today, you are positioning yourself at the very forefront of building the intelligent systems of tomorrow. Section 1. Your journey starts now. So there you have it. We've covered a massive amount of ground in a very short time. I know it's a lot to take in. We journeyed from the core architecture of the transformer, the engine that powers modern AI, the magic of the attention mechanism that gives it context. We saw how OpenAI scaled this up with the GPT dynasty. Prompt engineering became the new way to communicate with models. We tackled the memory problem, embeddings, vector databases, the game-changing RAG architecture. This is the new baseline for useful AI applications. We leveled up to the tools of the trade, LangChain, LlamaIndex, orchestration plumbing connecting all the pieces together, the API buffet, OpenAI, Anthropic, Google. We peeked into the future with AI agents, autonomous systems that reason, act, and use tools, coding assistant, content generator, research assistant. These aren't science fiction. You can start building today, 2024/5/24. Building with AI is no longer a walled-off discipline. Powerful APIs, open source tools, architectural patterns like RAG. The barrier to entry is lower than ever. The ceiling for what you can create is higher than ever. This is a paradigm shift, incredible opportunity. The question now, how? And by whom? The answer, you. This video gave you a map and a compass. The journey from here is yours to take. Read documentation, watch tutorials, write code, get your hands dirty. You will run into errors. Your first RAG pipeline might be slow. Your first agent might get stuck in a loop. Every error is a learning opportunity. Every failed experiment moves you closer to a breakthrough. The field moves fast. Be a practitioner, not a spectator. Start small, be persistent, and build. Section 2. Build, share, and subscribe. So what are your immediate next steps? Don't just close this video and move on. Your mission, should you choose to accept it, is to run a small lab. Pick one of the project blueprints we talked about. The simplest one is probably a RAG chatbot for a few of your own documents. Go to OpenAI, go to Anthropic, go to Google, get an API key. Many providers have free tiers to get you started. Grab an open source vector DB like ChromaDB you can run locally. Grab an orchestration library like LangChain. Don't aim for a production-ready app in one weekend. Aim to connect the pieces and see it work once. That aha moment. Ask a question about your PDF and the AI answers correctly. I've put links to everything in the description below. LangChain docs, LlamaIndex docs, API pages for major model providers, GitHub repos for vector DBs like ChromaDB. These resources are your new best friends. Their documentation is excellent and constantly updated. Dive into the Getting Started guides. They're designed to get you from zero to a working prototype fast. Don't be intimidated by options. Pick one path. Your first project is about learning the flow, not optimizing every single component. Share what you build. The AI developer community is vibrant and collaborative. Share on Twitter, share on LinkedIn, share on GitHub. Write a short blog post about what you learned. People will help and you'll learn a lot from peers. Building in public keeps you accountable and connects you to others. It's the fastest way to accelerate your learning and establish yourself. Don't wait to be an expert to share. Share your journey. If you found this guide valuable and want more deep dives, do the YouTube things. Hit that like button. Subscribe so you don't miss what's coming next. We're just scratching the surface. I'll be here breaking it down every step. Thank you for your attention. Now go build something amazing.